Hey everybody. So a couple of you were asking me about question 12 and 13 from the moments section of the course. So we're going to go through them now. I've got them done out here on my own copy, so I'm just going to talk you through my workings. So question 12 has two people who are carrying a metal rod with a mass of 15 kilograms. What upward force must each create to do so? So I've drawn out a diagram here that just shows the forces that are acting on it. If we were to try and just pick a random point in the center, I'll redraw a diagram over here, doing it the wrong way. If we were to just draw a random point in the center and we're trying to pivot it about that, you would think that would be okay because we'd be able to figure out from anti-clockwise forces equal to clockwise forces. We could just figure out what each of those are and let them equal to each other. But the issue there is that we've got an upwards force here that we do not know the value of. We call that F2. We've got an upwards force over here that we do not know the value of, and that's F1. So if we try to equate the clockwise and anti-clockwise moments, while that's good in theory, in practice we're going to have two unknown variables, and you can't solve a formula that has two unknown variables. Certainly that won't be something you're asked to do in physics for the Leaving Cert. I know you can do it in maths using a simultaneous equation. So we need a different strategy. So the strategy I'd propose is to get rid of one of these. And the way we're going to do that is by not having the pivot point in the center. We're going to have our pivot point instead directly over one of these areas here. So now this actually won't have a turning effect at all, because even though there is a force there, there is no distance from that turning point that we're looking at, right? So force times distance will equal to 0. The turning effect will be nothing. Then we've got a force acting here. We've got the weight of the metal rod pulling down here, which we know. So now if we look at the clockwise and anti-clockwise moments, this is going to be clockwise. We know it's force. We can figure out its distance from the diagram. This second force here is going to be the upwards force. We don't know that force, but we do know its distance from the diagram. So if we let clockwise and anti-clockwise moments equal to each other now, we'll only have one unknown, and that'll be our F2 here. So when I did this one out, I just copied out the diagram as closely as I could, and paid attention to where the different forces were, and made sure that I was just labeling those distances. Be careful to double check them, because if you do the distances wrong, which is easy to do, it will mess up your whole thing for you. The weight here is the downwards force. I put that down as 150 newtons, because I multiplied the mass which we're given, which is 15 kilograms, by acceleration due to gravity, which is 9.81 on the course, and I did a sneaky shortcut here. I multiplied it by 10 without really thinking. So I got 150 newtons. So later on you'll see that my workings aren't exactly the same as the back of the book, but the method is still spot on. So just when you're doing it out yourself, multiply it by 9.81. Multiply it by 9.8 if you want to get what they have in the back of the book. Multiply it by 9.81 if you want to do as well as you can in an exam, because that would be the standard they'd expect there. Then up here, the distance is 5 meters, and the force, I'm just calling it F4 because there's two women holding up the pole. There's one on the left hand side here, and there's one on the right hand side. So I just used the subscript or there to distinguish between the two, to make it easier, mainly for the examiner, my imaginary examiner, to read it. Okay. Right, I'm trying to get as many marks as I can here, so I'm writing out the formula, moments equals force times distance. I'm also just writing down stuff that I know, that is going to inform my calculations, right? So I'm saying that the clockwise moments are going to equal to the anti-clockwise moments. Right, then the force times distance, well, the force here is not visible. but we can call that F, or, right, the force from the woman on the right side. Her distance from the fulcrum is 5 meters. Then on the right hand side, the force, our weight is 150 newtons and is multiplied by a distance of 3.5 meters. This gives us 5 times F4 on the left hand side and 525 on the right hand side. Remember, if you're multiplying it by 9.8, then your answer is going to be slightly different, or 9.81. So this is definitely a case of do as I say, not as I do, because yeah, I was pretty much just taking a shortcut there that, you know, you shouldn't, because you're going to do an exam. Okay, the force on the right hand side then, we'll divide both sides by 5, and this gives us F4 on the left hand side and 105 newtons on the right hand side. If you look at the back of the book, like I said, it gives you 102.9 newtons as the answer for that, and that's fine. Again, that's just from putting in 9.8. To find the value of the force on the left hand side, you could repeat the whole process using your pivot pointers here, but it's not necessary to do that. There is an easier way. If you realize the entire weight is 150, well, I said 150 newtons, so I'm going to stick with it. 150 newtons. Then the weight holding it up should be the same, otherwise it'd be accelerating either upwards or downwards, which it doesn't seem to be doing. So if there's 150 newtons of weight that need to be supported in total, 105 of them are coming from the lady on the right hand side, then the remainder must be coming from the lady on the left. So we get our 150, take away 105, we're left with 45 newtons from the lady on the left, so she's doing half as much work about. Alright, question 13 then is pretty much the same thing. Again, I would just take a lot of care when you're doing it, the diagram. Take your time and make sure that you are doing the distances properly, because they give you loads of individual readings there. There's 1 meter, there's 6 meters, there's 2 meters. I think it can be pretty easy when you're taking things down there to just you know, try and rush through it, and you'll end up getting your measurements wrong. That's one source of error I could imagine being a problem for you. So again, I'm just going to treat one of the points that's being supported as a fulcrum. So then, even though there is an upwards force here, it's not going to affect that. It's not going to affect the lever in terms of, it's not going to have a turning effect about this point. So there will be a force, but the distance will be 0. So if we make the fulcrum here, then we only have the downwards force of the weight. It's going to create a clockwise turning effect, and we're going to have the upwards force of the second. They just call them support points in the question. So the upward force of the other support point there. Okay, so this time I learned from my lessons, and I put down, right, weight is equal to mass times acceleration due to gravity, and the mass we're given is 10 kilograms. The acceleration due to gravity is 9.8, right? Again, I probably would use 9.81, but I guess I just wanted to get the same answer as the book this time, so I put 9.8. So 10 times 9.8 is 98 newtons of weight here. We know the distance, so force times distance is something we can do. For the anti-clockwise, we know the distance, we don't know the force, right? So we have one unknown here, so we should be able to solve it out. Again, I'm just trying to, I guess, showcase some good behavior for you guys, how you get the most marks in exams. You just write down everything you know, really. So moments equal force times distance. I'm also just being really explicit about the fact that clockwise moments equal the anti-clockwise moments. I guess in a kind of a similar way to when we did the heat questions, and we said that energy lost equals energy gained. Because yeah, even though it's implied later on by you multiplying these and letting them equal to each other, it's just good to make sure that that's really, really clear to the examiner. So you're going to get as many marks as you can, and as many as you deserve. You're not going to be done ahead of them because maybe you didn't multiply one of these numbers out correctly. Okay. So our force times distance, well, force is, I'm just going to call it again F4 to say it's the right hand side force. The distance is 3 meters. and then the weight is 98 newtons times a distance of 2 meters. So 3 times F4 equals 196 we get. F4 equals 196 divided by 3 then. And that gives us force from the right hand side support of 65.333 newtons. If you're unsure ever how many decimal places to put in physics, just go with 3. And then for the force from the left hand side, we have pretty much the same thing as last time. Got the total weight of the log, take away the support we know is coming from the right side one, and the rest of the support must be coming from the left hand side support. So 98 is the overall weight, take away 65.333, and we're left with 32.667 newtons of force.